So this is a weird talk. Actually, the title looks pretty weird. I'm talking about NoSQL, and I'm talking about Postgres, and how to combine these stuff. Who's this crazy guy on stage? My name is Stephan. If you really want to go crazy, you can try to pronounce my last name. It's Hochdörfer. But you can call me Stephan. It's OK. As you can see by this really weird letter in my last name, I'm from Germany. I live there. I run my own company there. The company is called BitExpert. We're in business for the last 12 years. My current role is head of technology, which basically means I'm a kind of internal consultant. I help our teams to get the technology up and working and educate them and the like. If you have any questions concerning this talk, feel free to find me. I'll be here the whole day. If, however, you don't like or want to talk to a German, which I can fully understand, this is my email address, this is my Twitter account, so you can chat online. So that's me. So who are you? Who of you is using a relational database at work? OK, cool. Who of you is more the kind of the NoSQL guy? Yeah, just Derek, obviously. OK. So I think I covered both worlds in this talk. Let's get started. Thing is, relational databases are a kind of a relic from the past. They got invented in the last century. They solved our problems we had back then. But do these problems still exist today, or are we facing probably different problems? So that's a valid question that we need to ask ourselves. Who of you is still working in a traditional waterfall kind process model? No hands up, that's awesome. Sometimes I get 1 or 2 hands up, which is really weird these days. So probably you all do work agile, right? Who of you is working agile? Sort of, OK. Working in an agile environment and using a relational database can be quite complicated, at least when you think of agile as the customer has no idea what he really wants. And so in each iteration, you could probably change the whole schema of your application over and over again. And in this case, NoSQL gives us more freedom because we simply do not care about the schema in the database because we don't have any schema. Well, actually, when we're talking about document stores, which I assume in this case. I know there are a couple of other NoSQL stores, but for the sake of this presentation, when I say NoSQL, I mean document kind of stores. So the document store does not really limit us. We can persist any kind of object, retrieve it back, and just work with it. And we can change the objects, persist them again, and do not face any problems when storing that stuff. As it turns out, there are a bunch of NoSQL databases, some more well-known, like Couch or Mongo or Redis, some less known, like Hypertable, Hazelcast, Rethink. There is a website out there which is called NoSQLdatabases.org, which lists more than 150 different implementations, which gives us developers a really hard time figuring out which is the best technology for our problem, right? And as it turns out, like 10, 15 years ago, when you were a developer and you wanted to show your skills, you wrote your own content management system, right? These days, when you want to show off your skills, you write a NoSQL store. Or a dependency injection container, so depend, just kidding. We can classify these node databases into certain categories. There are graph databases like Neo4j, where you store your entities in a graph kind of structure. We got object databases where you persist the whole object and you do not need to use an object-relational mapper that we use to do these days. There are column-based stores. A fun fact, you can also use a column-based store in Postgres. There are a couple of extensions which allow you to do so. There is the ICMS extension, and there is CitusDB, which kind of simulate the column-like stores in Postgres. And we've got key-value stores, things like Redis and Memcache and the like. And we got the document stores, Mongo, Couchbase, whatnot. And we're mostly focusing on the bottom two during this presentation. So why does Schemaless make sense? Well, first of all, schema changes can be pretty expensive. There are a couple of relational databases which would lock the whole table when you do a schema change, which is probably not a big deal if you have just 100 or 1,000 records in your database. If you're as big as Facebook and you would try to do schema change, it will probably lock the whole application for a couple of years, which is probably not what you want. It definitely can speed up development because you simply do not have to take care of all this schema stuff. You just persist your objects as they come in. It's pretty efficient for stuff like continuous delivery because I really don't care about the database. I just deploy my application and it's working, hopefully. And most importantly, schemaless does not mean unstructured. Like most people say, well, schemaless, I have unstructured data, but that's not true. Like in a schemaless database, each record is structured by itself. I mean, yes, this product that I persisted like 6 months ago may look a bit different from the product data I'm persisting now, but that's not a big deal. Obviously, I have to take care of that in the application space, so I need to deal with these situations. So how can Postgres help us? Well, Postgres is sort of a glue. Who of you is using Postgres, by the way? OK, very few. So Postgres is a really old database. It came to life in the mid-80s. It got open sourced in the mid-90s. Currently, we are at version 9.4, which was released in December last year. And the pretty cool thing about Postgres is that it's super extensible. It has more than 300 different data types and a few, big air quotes, document type data types. So you can pick what you need and combine the relational part with the document store and get the best out of it. So depending on your problem, you could either store a document in a kind of document-orientated fashion or use the usual relational stuff that Postgres supports out of the box. But be careful what you do. There is this lady, Sarah May, who I think it's about 2 years ago published a blog post which was titled, "Why You Should Never Use Mongo," which, to be honest, it was probably not the best title because it's not really a problem of Mongo, but anyway. So she comes from this team called Diaspora, or she knows the guys who are running this Diaspora project, this distributed social network alternative to Facebook. And when the guys started developing Diaspora, they figured out, hey, which kind of data store should we use? And back in the days, it was said that social data is not relational. So they went the document path, and they picked Mongo. And they kept on developing and figured out, hey, we're having a few issues with how we store data, but we'll just go on and figure out how to solve these problems. And like a year or so later, they just stepped back a bit and analyzed what was going on. And they came to the conclusion that these problems only existed because they tried to emulate a relational database on top of Mongo, which simply is stupid. So what they did back then is they ditched Mongo, replaced it with MySQL, and it's been said that all their problems were gone. So it's really important to understand what you want to achieve with the data to pick the right data store. Back in the days, I really thought that there are two kinds of applications we are dealing with, at least in my company. We had these kind of like enterprisey applications where relations were really important. They were key to the domain, and more like the social community kind of applications where the relations were not so important. But after thinking about this a bit longer, I realized it's not the type of application that is important, it's what I want to do with the data. Do I really need these relations, or do I not need the relations? So you have to be sure which path you're heading and how important the data and the relationships between the data is to figure out which data store makes the most sense. So let's go back to Postgres. As I said, Postgres contains a few schemaless data types, which I'll cover in this session, talking about arrays, which is not really schemaless data type, but cool nonetheless. There is Hstore, there is JSON and JSONB, and there is XML. Oh yeah, I forgot to say, right now you will see a shitload of SQL. If you can't stand that, you're probably free to leave. but don't blame me afterwards. What's really interesting in this case is this term NoSQL was coined in 2009. The Hstore data type is in Postgres since 2003. Since 2006, there is the JSON data type. There is an extension for it. It got into the core distribution of Postgres back in 9.2. So for a long time, we have these crazy, weird data types, but no one really knows about it. So that was mostly the reason for this talk, to make you aware of what cool stuff is in Postgres. So let's talk about arrays. Guess you have heard of arrays before. Who of you is using arrays in PHP? I want to see all hands up. OK. Great. So you can have arrays in Postgres as well. And you can use arrays in combination for almost every built-in basic data type, as well as enums and custom-defined types as well. It's really cool to get rid of one-to-n relations. Let's say we want to write a blog application. No idea why, but anyway. In a traditional relational schema, I would have a blog post table, I would have a tags table, and I would have a relationship table which would map the tags to the blog post. That's 3 tables for a pretty basic problem, right? It looks a bit too much, and arrays can help us in this case. So let's get started. This is how you create an array column. So we create a blog post table. It contains a title, content, and an array of tags. So you just name the field, like in this case text, and then you just add these square brackets at the end to indicate that this is an array. You can also do multidimensional arrays. So if you do really crazy stuff, you can use that as well. As you can see, you can also specify the length of the array, like in this case it's 3 for both dimensions. Postgres right now does not check that. So I could make a 4x4 matrix out of that, or a 6x6. It doesn't really care, at least now. But this is, if I recall correctly, this is the closest to the SQL 92 standard as you can get. So you can, if you really want to be as close as possible to the SQL 92 standard, use the length. Having issues. Anyway, I'll just keep talking. So this is how you insert data. You have an array keyword. Crap. I'll just keep talking. So you got an array keyword. Would you grab my ear, please? Yeah. So this is an array keyword. You add these square brackets, and then you list all the items that you want to store. Like in this case, it's strings. Perfectly, thank you. I can store as many items as I want, so I do not need to have a fixed length for each of the items. It's important to know that this is an index-based array, so it's not a hash map like in PHP. Or if your SQL driver does not support the array syntax, you could use the angle brackets and list the keys as well. So this is probably the easiest to get in your client application. How do we select data? Well, it's easy. So we name the column, which is tags. We had these square brackets, and then we refer to the index. Given that we have 2 blog posts in the table, we select them. We get 2 results back, obviously. As you can see, the bottom one is empty. So usually we would get back a null value because we are just having 2 entries in this row. So you have to be careful what you do in this case. It's really important to know that arrays are one-based indexes, or use one-based indexes. So this is really the item number 3 and not the item number 4. This will really confuse you when we get to the JSON arrays, because it's slightly different there. So watch out. We can also use arrays for filtering for the where clause. Like in this case, show me all the blog posts where tag at the position number 2 is ipsum, which will give us both records. We can also search in an array. So there is the any function, or the any keyword, where we simply say, give me all the blog posts where any of the tags is named blog post, which will give me just 1 entry. If there is any, you guessed it, there is also all, the all keyword. Oh yeah, let's try this one. Okay. Feel free. Thanks. Anyway, okay, cool. Thank you. That's a lot of fun for this morning session, right? Anyway, so yeah, as I said, there is when there's the any keyword, there's also all. I have not found any good use case where I want to check if an array consists of the same value at all. Maybe there is one, I don't know. However, be aware that this can lead to performance issues, because what Postgres is doing in this case, it will go through all the blog posts and then check each array item, right? So this can be quite slow. That is a very good question. I'll come to that later on. So Derek was asking about indexes. Just wait, maybe 5 slides. So yeah, so don't overuse that. If you really need a relation in your database, then use that. Don't just go home and change all of your relations to arrays. That does not work. Well, it does work technically, but it does not make sense. We can also filter using the double ampersand operator, which is called the overlapping operator. So at least one element on the right-hand side needs to be contained in the tags, which will give us both back. We can also have, oh yeah, welcome to the weird looking Postgres operator world. So we got this add greater sign, which is the containment operator. So at least one of the items on the right-hand side needs to be contained in the tags array. So either lorem or blog post, which will, no, sorry, all elements on the right-hand side need to be contained on the left-hand side, which will give us just the one back that you can see. So every good blog post application needs a tag cloud, right? Because tag cloud is so Web 2.0. So how can we generate a tag cloud from that? Well, that's pretty easy as well. Hang on, I'll just explain that. So there is the unnest function, which will take an array and convert the array into SQL rows. So we convert all the arrays that we have into SQL rows, we group them by the tag, and then we do the count, which will give us all the tags and the count. So we have all the information needed to generate a pretty awesome tag cloud. And now we can answer Dag's questions. Can we use indexes? Yes, we can. Sort of. So we can create an index, a GIN index. So GIN stands for Generalized Inverted Index, on this array. And then if we do the containment search, we can see in the query plan that it will use the index for the scan. So we have a little bit of indexing for the arrays. How do we update arrays? Pretty easy. We can just overwrite the whole array, as we've done with the insert. We can update single items. So let's check that first. As you can see in my blog post, I should have used English titles. Sorry. So we got tag 1, tag 2, and blog post in the tags column. We can also update a single item by just referring to the index that we want to update, like in this case, setting tag number 3 to tag 3, which will give you this. Now to something really interesting. I can add almost any index that I want, like in this case 5. So the update will work fine. If we have a look what's the outcome of this, it will look like this. There is a null value for each index that was not set before. Yes, this means if I change the 5 to 50,000, it will generate a bunch of null values, which may or may not be good. And this only works for one-dimensional arrays. So in a two-dimensional array, this just doesn't work. You get an error back. We can also do a partial update, where we say the lower bound, colon, and then the upper bound of the items that should be updated. So the right-hand operator can be bigger than the bounds, than the length of the bounds. Then the items would be skipped. So we will pick the left item and then just go through the list till all the items were correctly updated. If you pass less items than you want to update, you will get an error for obvious reasons. So we got a bunch of, so we can see that's the final state. We got tag 1 to tag 5 as the name of the tags. There are a bunch of array functions. Array dims gives us a hint about the dimensions of the array. Upper and lower gives me the upper bound, the lower bound. I can grab the length. And I can build my own arrays using array prepend or an array append, so I can do some pretty hardcore magic in that case. Okay, so that's pretty cool. Now off to a more document kind of data store, Hstore. Yes. So Derek is asking if I can push arrays to the end of the array. Well, you could do using the array append function, like doing the update and saying I want to refer to this column as the first parameter to array append, and then just add the items. I never tried it, but that's probably the obvious solution. So Hstore. Hstore is a real, kind of document store. It's containing of key-value pairs, and keys and values need to be strings. Interesting fact, if during an insert and an update you pass a key multiple times, there is no real strategy which key wins. That sounds really interesting. I have no idea how this is implemented internally, if there's a kind of rand function or whatnot. I have no idea. So when you insert or update data, make sure that each of the keys is really there on its own. Hstore is the only extension that is not part of the Postgres core. So you need, on Linux, you need to install the Postgres contrib package. And then you open your database, and then you say create extension Hstore, which would register this data type or this extension with your database. And then you're able to use this data type when creating a database table. So in this case, imagine we're dealing with a products database. We are importing all sorts of product data from different customers. And these products look all pretty different. Like they have a few things in common, like a name, a price, a description, but then a bunch of metadata that we simply have no idea what's coming in, but we need to store it somehow. Traditionally, I could, again, use the N2M relationship and figure that out. But sometimes this can be pretty tricky, especially if, let's say, you want to version these products. Versioning an N2M relationship is really painful. So we want to store as much as we can in one table, and that's what Hstore is for. To insert data in Hstore, you could do it like this. It's basically a string, comma-separated values, and then we got key value and this little arrow that you probably have seen in PHP. Before. And so basically we pass it as a string and then cast it to the Hstore data type. Obviously we can filter data or filter items as well by referring to the single arrow and then specifying the key that we want to filter for and pass that as a string, because obviously, as I said before, keys and values are strings in the Hstore data set. We get both values back, black and red. As you can see, Postgres is not able to give the column a real name. Like Postgres doesn't know that the column should be color. You can use an alias as well if you're having issues accessing this information. If I access an element that is only available in a few of my documents, I still get all of my elements back, and the ones where the key is missing, I'll get a null value, which in this case is converted to an empty string because I'm using the Postgres console. I can also search for a key in Hstore using the question mark. So give me all the products where the key weight is available in the metadata Hstore, and it will just give me back the product that is matching the criteria. I can also do a search for a specific set of key and value combination using, again, the containment operator. So give me all the products where the color is set to red, which gives me just the one that we have in the data store. Similar to the previous example of the tag cloud, I can figure out all my keys that are existent in the Hstore by doing this bit of magic. So there is the Akey function, which, as the name implies, gives me back all the keys of an Hstore. in form of an array. And I use the unS function, again, to convert the array into rows. And then I do a select distinct to figure out which keys are uniquely in this whole set, and I'll get all the keys back. So this can be interesting for kind of drill down search, so I figure out what metadata is in there. And Derek is asking if this is always a full table scan. To be honest, I have no clue. That's the closest I can get. Okay. Again, we can deal with indexes. Gin index again, so we simply say create an index on our metadata column. And then again, if we do the containment search, we can see that the index is used in the search as well. To update in data store, fairly easy. We can override it completely replace it, or we could do a kind of partial update using the double pipe operator. So in this case, if the key weight is set, it would get overwritten in the metadata Hstore. If it's not there, it will be appended. If you can add items, you guessed it, we can also remove items, because that's probably what makes sense. We use the minus operator. So in this case, we simply say remove the key weight from our metadata array. The right-hand operator can also be an Hstore. In this case, it would remove the items which contain the combination of keys and values. So if this combination matches, it would be removed, which is pretty interesting, and I'll show you in a second why. There are tons of Hstore functions. As you've seen, there is an akeys function, which gives me all the keys. There is an avals function, which will give me all the values. I convert Hstore to an array. I can convert Hstore to a JSON, and have some more fun as well. So why is Hstore interesting? How many of you have implemented auditing in your application? Like figuring out who changed what when? Okay, quite a few. Was that an easy part? Yeah, sort of, okay. So obviously you could try to solve this problem on the application side, which can be a bit tricky or messy if you like, or you can figure out some crazy ways in the database to do so. Hstore by itself is pretty cool in this case. So what we do is we create a table audit. We have a timestamp for the change, and then we store the old value and the new value. Then we add a simple trigger, which would just populate the data by selecting or by converting actually the rows into Hstore elements. And then we bind the trigger to the database or to the database table that we want to audit. And what this gives us is this. I can pretty easily figure out what changed by using this minus operator. Because, as I said before, if both of the operands are Hstores, they will remove the matching key-value combination from both items. So it will just give me the items that are changed. Like in the first case, you see F1 changed to B, F2 changed to C. So this is super easy. Is it? Okay, no reaction. Okay, I'll go with that. Maybe you're just confused, I don't know. Anyway, so that's pretty cool. Okay, going a bit hipster, JSON. That always gets a laugh. Obviously, I can store JSON as a text field, and probably most of you have done that in the past, which is okay, but I mean, you can't be really sure that this stuff that you stored is really JSON, right? So the JSON data type really helps us with that. There is an RFC for JSON. Who of you knows the RFC number for this stuff? No one? Come on. Okay. It's 4627. I thought you know that stuff. Anyway, so there is an RFC for how a JSON object should look like, and Postgres adheres to that specification and just allows to store valid JSON objects. As I said, it's been available as an extension for quite some time. It came to the core distribution with 9.2, and it dramatically improved with 9.4, which I'll cover later on in this talk. So I don't need any fancy stuff. I just can say, hey, we have our table products, and the metadata part is now JSON, and that's it. Inserting stuff is pretty damn easy. You just have your JSON string, add it to the database, and that's it. You can add any kind of JSON as long as it's valid. Like in the first case, we add multiple keys, and the second one we have just the color red. That's no big deal. I can also change the color to be an array. That's also possible. So you're not limited in the structure of the JSON. As long as it is valid JSON, it will work. If you're passing invalid JSON, like in this case, trading commas, Postgres will complain and say, well, this is not valid data, I can't store it. That's pretty cool because you can be sure that the stuff that is in the database is really JSON. Obviously, we can query that stuff, we can filter it. There is a double arrow operator and there's a single arrow operator which would just select the item. So the double arrow one would convert whatever we query into a text string. Which gives me the colors that we are having in the database. As you can see, the last product has this array, so I, in my application, would need to parse that, obviously, to further process it. Yes, it comes back as a string. Very good point, Derek. I can also query arrays. This is really a weird syntax. So what we're saying here, we assume that color is an array, and we want to query the third item of this. Yeah, you're laughing, right? So this is not a 1-based index. We're back to the 0-based index to really confuse us. So again, we get back three rows because we have 3 elements in place, and only the last one is a valid array and has a valid element at the 3rd place. So we get back the blue one. Yeah, that's really weird. Anyway, again, we can use indexes as well. We can create unique indexes. So I can say, hey, I want a unique index on the color field of our metadata, for whatever reason. And then if I want to insert another product with the color red, which we already have in the store, Postgres will complain and just simply not allow that, which is really cool. I have no use case in that particular way, but anyway, it's really cool. It's really cool. Updating JSON, well, there's just one way. You have to pass the whole JSON object and the database. So you can't right now do partial updates. If I heard correctly, the Postgres guys are working on some crazy ideas of like partially updating the JSON stuff, but I don't think that it's already in there. So you have to pass the complete JSON object. There are a bunch of JSON functions. You could convert an array to JSON. You can convert a row to JSON. You can figure out the length of a JSON array. You can grab all the object keys and do much more. What's really, really cool is this row to JSON function, because it allows us to pretty easily create what I call a micro JSON web service. So this is pretty cool for prototyping. Like in this case, we say, select the row and convert it to JSON for the product with the name product C, which will give me back a valid JSON string. Remember, the metadata field itself is a JSON string, so it just gets merged into it. And we're dealing with a perfectly fine JSON result that we can easily just send back to the client. So no need for any fancy code in my application to figure out how to convert like the row to a JSON object or whatnot. In case you don't want to expose your exact data structures to the client, there is a simple, neat trick to work around that, and it's called subqueries. So in this case, we say, select this row to JSON T from, and then the subquery. And in this case, we're just selecting name and price, and we just get this back. And obviously, I could use an alias as well. I could just change name to title or whatnot, and the client would not know it. So this is pretty cool. I mean, you could easily write a 5 to 10 line code PHP script that would just act as a kind of JSON web service and just grabs the data from the database. So no fancy stuff needed on the client side. So that was JSON. Yes, Derek. One more back. This one?
All the values in the array are strings. I guess you can also use all the data types in there?
That is a very good point. So the question is, can I use all the data types in there? Well, you see, price is not a string.
Price is a top-level data type, right? It's not part of your JSON document in the original store.
Well, price was a column in my...
But I meant in the metadata.
Oh, in the metadata. Okay, very good point. You could use types, yes. JSON is type aware. So if you use... It should be, yes. Yeah. So let's go back to JSONB. So this was added in 9.4 specifically. And the B part indicates that we're talking about binary. Well, not how you communicate with the database, but how the database internally stores the JSON stuff. And the only difference is efficiency. That's probably the best way to put it. You have to use 9.4 for this. From the developer's point of view, it looks exactly the same as the JSON data type. So you just need to say JSONB when you create a database table. And then you can insert the documents as before. There's no real difference for that. If you do insert a JSON that is not valid, as we've seen before, you still get the same error back. So from your point of view, from the point of view of the developer, it behaves exactly the same as the JSON data type. But it does a lot more. First of all, again, we can use indexes. Again, the GIN index, which is super efficient for searching in our JSON fields. So again, you can use the containment operator to say, give me all the products where it contains a key color, which is black, which returns me obviously the right product. And if we run the explain statement, we can see that it will use the index as well for the scan. However, this only works if color is part of the top level JSON object. So it's somewhere down in the JSON tree, it doesn't work. That's probably way too complicated to do all the mapping. Anyway, we can also look up JSON keys by using the question mark operator, give me all the products where the weight key is part of the metadata, which will give me the right product back. And we can say, give me all the products where either the key weight or color is contained. So I can do searches there as well. Or if you say the question mark ampersand operator, it says, give me all the products where the key weight and color exists at the same time. So I can do quite some searches in there. So what's the difference between JSON and JSONB? Well, obviously the B part. So JSONB is really good for complex operations. As you can see, you can use this indexing part, which will really speed up operations. JSONB does need slightly more disk space than JSON, which shouldn't be a problem these days, but it's probably good to mention. If you just want to use JSON for storage, you use the JSON data type, because obviously the JSONB part has a kind of conversation going on. I mean, you take the JSON stuff that's coming in and you have to convert it to binaries, so there's a little overhead added to it, obviously. And depending on the operations that you do, it can affect the performance pretty much. And if you want to keep the original data structure that you send to Postgres, you should also, or you have to use JSON. So the JSON data type will store the stuff that you send to it one-to-one, while the JSONB one will convert it, and you have no idea what the stuff that you sent previously was all about. Fun fact, because Derek is over here, there are a couple of implementations which emulate Mongo on top of Postgres for whatever reason. So there is an implementation called ToroDB, there is Mongo-like, and there is Mongress, which are all kind of applications that sit before Postgres and emulate MongoDB, like they speak the same protocol as Mongo, so the application doesn't really know that it's not Mongo, and then they use the JSON data types to store that stuff on Postgres. So if you want to experiment with that and annoy Derek, you can use these kinds of things. Anyway, if you're more the enterprise developer, you probably think JSON is way too hipster, and then you can go the XML route. Basically the same as JSON, you can store XML in a text field for whatever reason, which we probably have done over the last years. The XML data type does a bit more. It will check if the XML is well formed. It does not do a DTD check, or it does not do an XML schema check. It simply checks if the XML looks well formed-ish. XML is part of the core, which basically means you can just use the data type as is. Just say, hey, we got a column named content, which is part of, which has the data type XML. So I'm not sure about you, but we have sometimes customers from the enterprise field which come up with some crazy solutions when it comes to application talk to each other. Like one of them invented the famous XML over FTP protocol, which is as crazy as it sounds. So our application had to connect to an FTP server, download the XML stuff, and then process it. And like we stored it using this in Postgres. So we did not store it on disk, but just in the Postgres database. As I said, you can store any kind of XML. Does not really matter. You can have attributes, whatnot. It just needs to be well formed. If it's not well formed, like in this case, we are missing an closing open tag, Postgres will complain and say, hey, this is not well-formed XML, I can't store it. Obviously, we can query XML. Unfortunately, there is just one way to do it, and we probably all hate it, XPath. Oh, okay, great. Yeah, so you can use any kind of XPath expression in there. In this case, we want to figure out the product nodes in the order and grab the ID attribute, which will give us this back. We get a bunch of arrays back for each set of XMLs that we have found. And you probably do remember the tag cloud example from the beginning. Like this is an array, as you can see with the curly braces. We can do some really fancy stuff with that. Something like this. Hold on, I explain. Don't run away. So what we do here is, again, we have the XPath expression, which gives us all the IDs of all the products that were ordered. We get an array back. We unnest this array, like we convert it into SQL rows. Then again, we group them by the product ID, and then we count them, which will give us a nice little statistic about how often a product was ordered in all of these XMLs. Now, this is pretty neat and pretty simple. Think about how to solve that if the XML was stored on disk. Like you need to scan the whole directory, open the XMLs, parse them, do the XPath, do the calculations and whatnot. This is literally a one-liner of SQL code, which is really amazing, at least in my point of view. We can also figure out or use the XPath expression in the work clause, where you can say, hey, show me all the imports where a certain XPath exists. So that's what the XPath exists function is for. Again, provide a valid XPath expression, and then we get the imports back that match. So if you want to do a quick search on a certain product, you can do so pretty easily. If you remember the micro JSON web service I showed you before, you can also do the more enterprisey version of that using the query to XML function. You simply pass a select statement and a few flags, and then Postgres will spit out a bit of XML code, which you then either can convert using XSLT to another structure or just echo back to the client as well. So again, pretty easy, pretty simple to write just a simple web service for testing purposes. We have a bunch of XML functions. There's XML concat to concatenate XML strings. We got force to produce a sequence of elements. an aggregation. We can figure out if the XML is well-formed. We can, as you have seen, create XML from a query function. We have XPath and a bunch of others as well. So that's it for the data types. Now, NoSQL in most cases means a lot of data. Obviously, it's not just having no structure or whatnot. It means dealing with a bunch of data, which sometimes is really hard to deal with in just one table because performance, obviously. So you can partition your database tables as well, and like splitting one table up into multiple physical ones, just to increase the query performance. And it's also pretty easily done in Postgres. You simply create a master table. In this case, a table containing all the sales stats. And then we create like child tables, where we simply say the child table sales stats 2012 and 2011 inherit our master table. And we need to add this check this check instruction so that Postgres will know where to look when a query contains year 2012 or year 2011. So Postgres in this case will exactly know which table is the target table for a specific search. Because in our application, we just interact with the sales stats table, with the master table. So our application has no clue that we have some child tables in place. Then we add a little fancy trigger, which doesn't really much. It's really weird looking, but it's really easy to understand. So first of all, we figure out what year it is. What's the current year? Create the table name from that year, and then the bottom 4 lines just figure out if this table exists in the Postgres catalog of tables. If it does not exist, we simply create it, as you've just seen, and then we just insert the data into that specific table. So this is really cool because our application just interacts with one database table, with the master table, and Postgres internally like redirects the reads and writes to the correct tables, whatever correct means. However, this only works if we pass the year as a filter element, because then Postgres exactly knows which table to search in. If you omit the year, Postgres would search across all the tables, which can take quite some time. Other than that, oh yeah, we have to register the trigger as well to make things work. Other than that, Postgres is pretty awesome. It has way more stuff to offer. The damn coolest thing ever are the foreign data wrappers, which basically means I can expose any kind of third-party data store as a Postgres table in my Postgres database. That sounds weird, but it basically means I could expose a SOAP web service, another Postgres instance, a Redis server, or whatnot as a Postgres table in my local database and use that to join my local data with it and do some fancy stuff. So that's really cool. In addition to that, we have a range data type to store ranges in one column, which is also pretty neat for searches. Yeah, we got stuff like materialized view, conditional indexes, and a bunch of other cool things. Postgres by itself is a pretty large ecosystem. As I said, it's been around for a couple of years. We have tons of backup and recovery solutions, clustering solutions, replication stuff, administrative tools, whatnot. So it's a proven technology, and there are a bunch of little Postgres users out there, companies like Instagram, Reddit, Skype, Etsy, and the like. So you should try it out. Thank you. And before we go into the question mode, just one final note. Please go and join in, rate this talk. I'm pretty curious for feedback. So that's it from my side. Any questions? Yes, one in the front.
Hi, I have a question about 2 data types, the Hstore and JSON.
Yes.
Those 2 looks for me very similar, and JSON seems to have all the features the Hstore has. So is there an advantage of using Hstore over JSON?
That is a very good question, and I missed this point in my presentation, so thanks for asking. So JSON basically is just a simple, like one-level store. Like you have key and value, and the value is just a string. If you need like a complex structure, you have to use JSON. Like the key can't be another Hstore or whatnot, so it has to be a simple string. So that's probably the biggest difference.
Okay. Thank you.
Okay. Anyone else? Go ahead.
Anyone? No, that's it.
No questions.
Oh.
That's great. Oh, there's one.
I have a question. What about support for things like arrays in PHP mappings?
So you mean how to deal with the data when it comes back?
Yep.
Okay. So that pretty much depends on the data access library that you're using. If I recall correctly, Doctrine has support for arrays. Maybe JSON, but I'm not really sure. So this really depends on your library that you're using. Like in most cases, this stuff comes back as a string, and you then have to manually convert it back and forth. Hang on.
Sorry, how does the performance compare to, say, Mongo?
Depends who you ask. There are some Postgres core contributors who did a comparison, and they say that Postgres is more performant than Mongo. It probably really depends on the use case and what you want to achieve. And as always, you have to measure it for yourself. That's probably the most accurate answer I can give. So it was always fast enough for us, but in most cases, we are dealing with small applications and not like the big data stuff.
No, that was my question. That was your question.
Oh, that was okay. Cool. That was an easy answer. Anyone else? One over here.
Hi. Is it practical to store like thousands of key values in an Hstore, or does it quickly come to a point where it's better to be using a separate table?
It probably also depends on what you're doing. Like if you're just storing, it should be a no-brainer to do that. If you do like complex searches, I have no idea. You're probably doomed. But anyway, since it's a binary store, it's actually pretty good, Derek says. Okay, so it's a binary store, so it should be pretty much optimized for that. At least compared to the raw JSON one, which, oh, I forgot to mention, yeah. So the big difference between the raw JSON one and JSONB is that the JSON one is actually parsed that each time when you access the column, like it's parsed by the V8 engine, which adds a certain overhead. So in that case, it would really be a performance penalty. But Hstore, yeah, I would suppose that it's just fast enough.
Cool, thanks.
That's it.
One more, there's one more free. No one? Okay. So that's it for me. Thank you.